Good evening. Welcome to the National Air and Space Museum's Exploring Space lecture series. I'm Matt Schindel, curator of Earth and Planetary Science in the Museum's Space History Department, and it's going to be my pleasure tonight to host this evening's discussion. This year is the 50th anniversary of our museum building here on the National Mall in Washington, D.C. And for this year's series, we're taking inspiration from the gravity-defying technologies featured in our newly reopened Milestones of Flight gallery. Tonight, our discussion will be inspired by a historic mission, the first successful interplanetary spacecraft, Mariner 2. In 1962, Mariner 2 flew by Venus and returned the first ever data from another planet. Today, Venus exploration continues. More spacecraft have visited Venus, sent back data from orbit, and even landed on the surface. NASA's plans for the future include even more ambitious missions, and they're not alone. We have two remarkable guests with us this evening to discuss the past and the future of Venus exploration. And before I introduce our guests, I'd like to take a moment to thank the sponsors who make these events possible, L3Harris Technologies and United Launch Alliance. Our guests tonight include Sarah Seeger, who's a professor of physics, planetary science, and aeronautics, and astronautics at the Massachusetts Institute of Technology. Her research spans the foundations of exoplanet atmospheres, theories about life on other worlds, and the development of novel space missions, including leadership roles in NASA's planet hunting mission TESS, and the Asteria CubeSat, and the Morningstar mission to Venus. Our other guest tonight is Bruce Campbell, a senior scientist in the National Air and Space Museum's Center for Earth and Planetary Studies. His research focuses on the surface and subsurface geology of the Moon, Mars, Venus, and the icy moons of the outer planets, resulting in more than 100 scientific publications. He's a science team member for the radar sounder instruments on the Mars Reconnaissance Orbiter, the Jupiter Icy Moons Explorer, and Europa Clipper, and he's co-lead for the imaging radar on the Veritas mission to Venus, and a team member for the Da Vinci mission to Venus. There's a lot more that I can say about our guests. They're both incredibly distinguished and accomplished, and we're going to have the opportunity to get into more of that in our discussion. But before we dive into our discussion on Venus, we'd like to take a brief moment to highlight the museum's 50-year history with a brief video.
This beautiful new museum and its exciting exhibits of the mastery of air and space is a perfect birthday present from the American people to themselves.
In 1976, we open our doors on the National Mall in Washington, D.C., taking our visitors on a journey through the sky and out into space.
Shall we touch a piece of the moon?
For the last 50 years, we have welcomed hundreds of millions through our doors, conserved, restored, and safeguarded priceless artifacts, brought history makers to you, opened new exhibitions, acquired new artifacts to document the past, present, and future of aerospace, and helped inspire a new generation of innovators and explorers. The last 50 years have been incredible. We cannot wait to see what the next 50 years hold.
All right, so we're going to start with a couple of questions that hopefully will allow you both to introduce yourselves a little bit further by asking you essentially how you got here tonight. So Bruce, you've spent a lot of your career, or most of your career, maybe all of your career actually, using radar to penetrate the thick clouds of Venus as well as to look at other planetary bodies in our solar system. What would you say are the major findings from that work, and sort of how did that sort of lead you to your participation in Veritas and Da Vinci?
Well, I think what always, just to go back to the beginning, I was very fortunate that the summer after I got out of college, I had a NASA internship at a place where they were seeing the first of the Venera 1516 radar images of Venus. And so that was an opportunity to really, for the first time, see some of these landscapes, see some of the mountain ranges, other features that were just amazing to see and all hidden by the clouds. And so I thought that was just great, and gradually got more and more into working on Venus data from Earth-based radar, and then eventually working on Magellan data and additional Earth-based radar as we went along. So I think the overall picture of Venus is simply just a mystery, always hidden by the clouds, but we have those tools to be able to look through the clouds and to understand this mysterious place.
And Sarah, you've spent most of your career focused on exoplanets and their atmospheres and the search for other Earth-like planets. How then do you turn to Venus? Can you walk us through your path?
Well, I was working on exoplanets for 30 years, planets that orbit stars other than the sun. And we're truly in a golden age for exoplanets because we have the James Webb Space Telescope observing their atmospheres. And the planets are so diverse and so amazing. And we're trying to find signs of life on exoplanets by way of gases that don't belong, like oxygen and, well, not oxygen with the Webb, but many, many gases. Anyway, just to make a long story short, one of my favorite gases that could be a sign of life is a gas called phosphine. And if there's any space fans out there that have followed Venus, we were part of a team that reported a discovery of phosphine gas on Venus, of gas that shouldn't be there, Well, it's incredibly controversial as to whether or not it's there, and if it is there, whether or not it could be a sign of life. But phosphine drew my attention to Venus, and a lot of other people as well. And I realized, I don't know why I didn't know how great Venus is. It's not just the surface and everything else, but the whole entire planet is so intriguing, and I've been hooked ever since.
I want to let folks know as we get into this conversation, if you have a question while we're talking, we will have a Q&A after our discussion. And in order to submit questions for that Q&A, there's a QR code right now behind me. You can use your phone to scan that code and submit your question. Or if you're watching online, you can put your questions in the chat, and those will come to me here on this iPad along with our audience questions. But for now, I get to ask my own questions. And one of them is going to be a historic question. So, this lecture tonight is inspired by Mariner 2, which, as I said in the introduction, in 1962 became the first successful interplanetary mission, which is why Mariner 2 is hanging out in our Milestones of Flight hall. What did we know about Venus before we started sending spacecraft there? And how did Venus surprise us?
Well, prior to Mariner 2, we understood that there was a lot of thermal radiation, that something was hot at Venus. And there were discussions about whether it was solely the surface that was hot or whether there was some possibility of, say, a hot ionosphere or something else that would sort of fool the radio measurements that were suggesting that there was all this heat coming off. So Mariner 2 carried a package of instruments, both microwave and infrared radiometers, and those instruments were able to definitively say that, yes, the surface was hot, and in fact, in the neighborhood of 800 degrees Fahrenheit. It also showed for the first time that day and night were essentially equivalent temperatures on Venus. So it's a very quiet, hot, slow-moving place. If you're right down at the surface, the wind blows very gently west to east all the time at a sort of slow walking clip. The temperature doesn't change much day to night, and you don't really know where the sun is in the sky. It's simply lit up from all directions. So Mariner 2 really took us in those directions toward learning those basic facts about what the surface is like.
And at the time also, people were trying to figure out what the clouds are made of because they're very, very bright and reflective. And that's why when you look out at Venus, it's incredibly bright. And I guess at the time or before the 60s too, people maybe perhaps wanted it to be water clouds like we have on Earth, but they had evidence that it could be water, it could be other things, could be sulfuric acid. And although Mariner didn't help weigh in on that, that's kind of where we were at the time.
That sets up, I think, a pretty good, segue then into the question of Venus and how different it is from Earth, because in many ways Venus is very similar to Earth. It's similar in size. It's our pretty near neighbor in the solar system, but yet it took such a different path, I guess, evolutionarily as a planet. What have we learned about how Venus became what it is through exploration?
Well, I think you're hitting on the sort of theme that everybody comes back to, and just to sort of jump ahead to it, at some point, did Venus have an ocean? Where did that ocean go? When did it go away? And are there any traces of that period left in the surface geology or the atmosphere that we can try to address that question?
I'm curious if you have a scientific opinion right now whether or not you think Venus had water at some point.
Climate science is definitely not my area of expertise, but I think there's every reason, just from forming in the same part of the solar system and having the same influx of comets and sources of water. I think and we know that there are terrains on Venus that appear to be older than others. And so the big question for me is, if you assume that there was a period of time when there was an ocean, is any of the geology left over from that? Does it carry any kind of trace of that period of time and some indication of what the geology and what the processes on the planet might have been like before the period that we see?
We've spent a lot of time exploring the surface of Mars with rovers. Venus is a much more difficult planet to land anything on, and yet there have been some successful landers in the past, the Venera landers, for example, from the Soviet Union. What have we learned from being on the surface, and is there a way to spend more time on the surface or near the surface in future missions?
Yeah, what we learned, the thing I like to say about the Venera photographs is, essentially you have to know a world from 4 postcards, because this view, we have 4 of these from 4 different places. You're looking through basically a fisheye lens, where the area right in the center of the image, you can see the spacecraft edge at the bottom. Those rocks in the center are very close to you, and then the horizon is out in the upper right and upper left corners. And so from 4 of these pictures, mostly on relatively flat areas of the planet, not in the mountains, we have to try to infer something about the geology. We know that the chemistry suggests that a lot of it is basaltic rock, like we see from volcanoes on Earth. We also have the measurements of that very slow-moving wind. We know that there's what is probably likely a very aggressive chemical weathering regime because of the atmospheric chemistry. So we know that it's probably forming fine material out of the rocks, which is what you see in between some of the rocks here. But the big question is, for some other studies, is does that stuff stay in place? Does it get transported? Do other processes bring fine material down into your neighborhood from elsewhere? So it's been a challenge to explain what we see at the Venera sites, but we are very limited, and this is a sort of counterpoint to the other one. If we go back to that prior picture, the interesting thing to me about this, there were 2 cameras, one in front and one behind. The camera cap did not work, did not come off on the picture behind this. So we know we're on a 20-degree slope and we're looking downhill. And the question is, what's behind us? You'd really like to know if you're on a mountain, if you're right by a cliff. We don't know. So there's obviously need to go back and try to see more interesting areas.
It's hard to be on the surface of Venus. It's so hot, as you started out saying, 700 degrees Kelvin. So we'd have to have a whole new kind of electronics that could withstand that heat if we wanted to stay on the surface longer than those past missions of like 20 minutes or an hour.
And, getting away from the surface for a second, Sarah, you're interested in the atmosphere and the clouds and what you might find there. Get us excited about those clouds. What are you looking for there?
Well, the whole reason I got fixated on Venus, it's the thing how on Earth, when you go above the surface, like on a mountain or in an airplane, it gets colder and colder. And that's true on most planets. And on Venus, 50 kilometers above the surface, it's the right temperature for life. It is like our temperature here and like the pressure here. And this is why over half a century ago, Carl Sagan first put out the idea that maybe there's life in the clouds of Venus. There's life in our clouds here on Earth, bacteria temporarily swept up, but our clouds are very fragmented. And in Venus's favor, those clouds are always there. They're photochemically produced, they are covering the entire planet, and they're very, very deep. So it's kind of a really interesting thing to wonder, just as people have kind of thought about this ever since, that maybe there's like tiny life, like bacteria, just barely eking out an existence.
And I know you've done some chemistry experiments to see what could survive in those
one thing,
clouds.
we could start with the video. I want you to know why people think life couldn't survive. And so we're ready to show the video. Well, the thing is that our life can't survive in sulfuric acid, partly because our DNA is rapidly destroyed. So instead of putting life or DNA in sulfuric acid, what the clouds of Venus are made of, acid, concentrated sulfuric acid, this experiment is showing you sugar as a representative for DNA because we have a sugar phosphate backbone. Now watch what's happening. That sugar, just like you'd have in your house with sulfuric acid, is rapidly changing. It's hot. There's hot water vapor coming off. And that sugar, remember, this is a proxy for life, proxy for DNA for life. Look what's happening to it. It's actually getting all the water sucked out of it, dehydrated. And on the other side, you can see an infrared image. It's hot. It's really hot. So how do you feel about life in the clouds of Venus?
It doesn't look very comfortable.
And so there's no possible way our DNA can survive. That's the bottom line. Sugar was the proxy for DNA, proxy for life. And you can understand why this throws people off. It makes no sense that any life could survive and it can't. However, my team started to do experiments in concentrated sulfuric acid. And we asked ourselves, could we come up with a DNA-like molecule? Not our DNA, but swapping out parts. What if the one part that is reactive could be replaced by something that's not reactive? And after a couple of years, we actually came across a molecule. It's a DNA-like molecule. And it's not called DNA, it's called PNA, peptide nucleic acid. It's something biologists use already. It doesn't exist in life or anything. It's just a similar molecule. And we're hoping to make a lot more progress. We're hoping to find a molecule, we're hoping to show that there's a molecule that can make a double helix. Maybe it's this one, maybe it's another one. But it's really just the tip of the iceberg. We have put amino acids and small peptides and lipid and like tons and so many different molecules. And it's fair to say that some molecules are unstable and get ripped apart, just not as violently as that sugar did. But I just wanted you to all know that there's a growing number of biomolecules like building blocks of life that are stable in concentrated sulfuric acid. And some of these building blocks, we know they're in outer space. They're on the asteroid Bennu, part of that we brought back, NASA brought back to Earth and found some of those molecules in Bennu. So we know they're being delivered to Venus, and we know the building blocks, some of them are stable in the clouds of Venus.
That's fascinating. And Bruce, we've been talking a lot about spacecraft exploration of Venus, but you've used a lot of ground-based radio telescopes, like in Arecibo, for example. I wonder if you could tell us, why is radar such a valuable tool in studying not just Venus, but the solar system?
Sure. I mean, for Venus in particular, radar simply can see through the clouds. The same way a radar can see your airplane coming into the airport in the fog. Radar is a long wavelength type of radiation. It can probe through the clouds. But even on Venus, Venus will sort of fight back to make sure you use a long enough wavelength of radar to get through that dense atmosphere. It's not an easy thing to do. You have to have a particular type of radar, and you have to have, if you're on the Earth, you have to have a lot of power. 2 million watts is a good number to use to get a signal off of Venus and to make a map. Oh, and this is a map, if we go back one, that's an Earth-based map. That area in the middle is a single gigantic volcanic source, a corona. It's about 600 to 800 kilometers across, that set of lava flows that fan out toward the bottom. It's a good example of, A, what you can do from Earth, but also the scale of the volcanism on Venus. Just phenomenally large volcanic constructs that form very, very long flows. And this, of course, is what all of us would like to understand. I believe, and I think a lot of people believe, that Venus is very active. And the next set of missions and exploration is to really get into it and understand where that's happening, how quickly it's happening, and how that fits into that picture of how we got to where we are today.
Just a reminder for folks that if you do have questions, there's a QR code that you can use to submit your questions. And again, if you're watching online, please put your questions in the chat so that we can have those when we transition into the audience Q&A. This is a question for both of you. Obviously, you both have really, questions that you're very interested in putting Venus to, to answering with Venus. And you're both also involved in upcoming missions and missions that are, either in design or on their way to the launch pad. How do these questions help to shape those missions and the instruments that you're including?
Well, in this whole idea, we want, in the laboratory, we've shown that complex organic molecules can be stable in concentrated sulfuric acid. And we'd like to go to Venus and go in the clouds and try to find out if the complex organic molecules are really there. And our whole goal would be to find molecules so complex that they shouldn't just exist on their own, but that they could be a sign of life, because life is made of very, very complex molecules. So it totally shapes the mission to kind of set your science goals. And sometimes, the science goals exceed the cost that you have available. But we do our best to try to get to the heart of what we are trying to find.
Yeah, I think that's a very good the way to look at it. You have a certain set of constraints about your engineering and your cost and your capabilities, but you really have an opportunity every so many years to be able to look at what you know, try to refine those questions, understand what the community as a whole wants to know, and then ask yourself, with what I have in hand, how do I go ahead and address those? And I think the missions that we do develop end up asking really sharp questions and have a chance of answering them.
And one really interesting thing about missions, maybe it's obvious, maybe it's not, but you have to plan everything extremely carefully. And we make these giant charts, we call them science traceability matrix. And you have to kind of write out your goals that get sharper and more well-defined, and then exactly what you need to measure, and make sure that the instrument can actually measure it. So everything is all really tightly written out, and you better make sure you wrote it properly, because when the engineers come by, they don't read the whole thing. They just go to the last couple of columns and build what you said you needed to get built.
I think two of the aspects of planetary exploration that have really captured the public's interest are the search for life and also the search for planetary systems around other stars and the search for other Earths. I think we've already talked a little bit about how Venus fits into the search for life, but what about the search for other Earths? Are there lessons we can take from what we've learned from Venus that we can apply to that search?
Huge lessons. For one thing, if there's an alien civilization out there around a planet around a nearby star, and they're looking back at our solar system, it's kind of shocking to think, but they couldn't find Earth or Venus right now. But if they're having like our next generation telescopes, like NASA's Habitable Worlds Observatory, they could see Venus and Earth, but they might not know which one is habitable. I mean, let me backtrack on that. They could know Earth was habitable, but Venus, because it's so cloud covered, we wouldn't really know what's there. And I think with Venus, if we look in history, like we were talking about before Mariner, we had hints. It was hot, or we had hints of this, or hints of that, or hints that might not be water clouds. But one of the things with exoplanets is sometimes we're left at hints. We can't get any more. So I think the lesson is just how different Venus and Earth are from each other. And that for exoplanets, we can't really be constrained by just narrow-minded thinking.
Yeah, and certainly within our own solar system, you know, you get to a point where it's you say, well, we understand so much about planetary processes. We understand the processes that led to the formation of the moon. We understand the geologic history of Mars, the history of water, the ice caps. But then you come to Venus, and there are just fundamental questions about major landforms that we cannot answer, that we don't understand how those landforms formed, why they're there and not on other planetary bodies. And in a sense, you're trying to round out your understanding of a solar system, the one we have to study, and there are mysteries there that we need to solve.
So if you really need radar or to go down through the planet atmosphere to see the surface, that means if these aliens are out there, they know nothing about Venus, right? Because they can't use radar and they don't have a way to like get to the planet. So it's tough. If it ends up being that Venuses are more common than Earth-like planets, it's not as satisfying. It won't be as good because we won't be able to tell much about them.
Yeah. And correct me if I'm wrong, but we found a lot of very hot exoplanets at this point, yes?
Well, at this point, because of selection effects, like it's easier to find planets close to the star. So we have found a lot of hot planets. And what's so fascinating is we're just hearing how different Venus is from Earth. Surely there have to be exoplanets that are that much different from Venus and Earth. And we're starting to find those planets. And so it's pretty exciting.
I want to bring up the first lecture in this series this year was about the Pioneer plaque and the Voyager record. And connected to that is the famous Drake equation, which is a way of calculating what the likelihood is of two technologically advanced civilizations contacting each other across the stars. Sarah, you've come up with your own version of that equation. Can you walk us through it and why you felt it was necessary to have a new equation?
Sure. Yes, I took the Drake equation and revised the Drake equation. And don't worry, I asked Frank Drake if he minded after I did it. He said it was fine. He was a generous person. But the Drake equation, if you remember, it was designed to illustrate the different factors that go into the search for intelligent life that would be sending us a radio signal. But because of exoplanets and having thousands of exoplanets and our human journey to remote sense and use our telescopes to try to find signs of life, I took the Drake equation and I redid it for the search for signs of life, not from communication from radio telescopes, but from signs of life by way of biosignature gases. So the number out there would depend on N star, the number of stars in your survey. And I built this around the TESS mission, the NASA TESS mission that launched in 2018 and has found lots and lots of exoplanets. And FQ really meant the ones that are quiet enough, that are not like varying in brightness, so that we can find planets around it. FHZ was the fraction that have planets in their so-called Goldilocks zone or habitable zone that are the right temperature for life. And FO were just the ones that had the right geometry that we could see what are called transits. But just to zoom out a little, just like the Drake equation, it's meant to illustrate. And the first three F's fractions are things we know. We can actually quantify those. But just like the Drake equation, the last two, they're just speculative. What are the fraction of planets that have life? And if they have life, what are the fraction, can we just go back? What are the fraction S that have a spectral signature? And those two we don't know. And so if we wanted to think of the TESS mission and the James Webb Space Telescope observing the atmospheres of those, you can sort of like play around with the numbers and be optimistic. And the number that might be, have been found by TESS that might have signs of life, that the life gives off signatures that we might see, is 1? No, it's just not really a real equation. It's not a real number, but it's just a way for you to like factor out all the things you need in order for us to be able to find a sign of life on a planet in the near future with the test planets and the other exoplanets we have in hand.
Thank you. Bruce, you've spent, your career connected to Venus exploration, and you've seen how, that has progressed. I wonder if you, and you as well, Sarah, if you could draw your own roadmap for the next 10, 20 years of Venus exploration, what would it include? What would that roadmap look like?
I guess from my point of view, I mean, we have good missions in the pipeline. We're going to do Da Vinci. We're going to do Veritas. Those between them are going to answer a lot of fundamental questions about sort of global properties, global topography, potentially differences in the rock population. But in the end, to really answer these questions, we have got to go back to the surface, and we really have to go back in a way where you can have humans in the loop. The thing right now is that most spacecraft are going to live a few hours, say, in that neighborhood. There's not enough time there for you to look at the picture you see in the camera, take your robotic arm, say, and do science on that rock, that I want to see that rock, or I want to see this spot on the ground. There's not enough time to interact in that loop. And so we need to develop high temperature electronics, some degree of capability maybe to move, but to be able to get down onto the ground in interesting areas that we've defined from orbital studies and do the kind of work that we do for Mars sort of routinely now from rovers and landers. We need to take those next steps toward high temperature capabilities and being able to just answer the fundamental questions on the ground.
I thought you were about to say that you wanted the rovers on the ground that could operate, but then humans in the loop would be like in the inflatables floating around in the atmosphere.
Sounds good.
Sounds good.
I could imagine yachts floating in the clouds.
Yeah.
I think,
Think
sort
so.
of a fancy space station.
Wow, okay. And
I
they're-
didn't even know that image was in the queue. Thank
Nice,
you.
Nice. Yeah. Well, in the search for signs of life beyond Earth, whether it's on an exoplanet or Mars or a solar system body, there's a debate about where's the line between molecules that would occur on their own from like geochemistry and, atmospheric science, physics and chemistry, and where a molecule has to be so unusual that it is a sign of life. And people debate where that line is, and it keeps moving around. Because I could say, wow, I have this complex organic. I think it's got to be only made by life. And Bruce could be like, no, here's a way that we can make that with photochemistry. Or on exoplanets, we're like, wow, here's a gas that might be by life. And then someone else says, no, this exoplanet could have an interior that has a lot of hydrogen, and therefore you're wrong. So there's sort of, I don't know if it's an inkling or like a sure thing yet, but there's this growing unfortunate that in order to really prove there's life beyond Earth, we need sample return in our solar system, from objects in our solar system. So when it comes to Venus, the idea is to bring back, to collect clouds. Like, how when fog collects on your coat on a foggy day? But like to have fog collectors and collect the cloud material and get it in a canister and get it back to orbit and have the orbiter bring it back. Wouldn't that be so amazing if we could be here in the future and be like, yeah, here's my vial of Venus cloud particles. Yeah. So we want to bring it back. And, Mars sample return is something that has been taken seriously. And we've brought back part of an asteroid, and Japan has also. So it's within reach, but not until we get there and show there are these complex molecules and other things. So wouldn't that be amazing? We can go to the surface, we can study the whole atmosphere, bring some gas and clouds back.
Yeah, that'd be amazing. I'm a big fan of all kinds of sample return, I have to say. So I'm down for it. I want to remind you all again about the QR code. I know it's up behind me right now. If you have questions, we're going to be transitioning to Q&A soon, so get your questions in. I want to ask you both, the sort of, human-centered question here. What does Venus exploration tell us about our place in the solar system, our place in the universe, our planet? What do we learn about us from studying Venus?
Well, I think it tells us we're just lucky. We're lucky we're Earth formed, wasn't too hot, it wasn't too cold. And I think that's pretty sobering.
Yeah. Well said. Yeah.
Thanks, Bruce.
No, I think yeah, there is that type of question, but there's also, to me, just it's the fact that people want to explore, people want to know. There's an unknown here. There's a mystery at a large scale, that there are things we don't understand about a planet as large as our own, as similar in formation and location in the solar system, and yet it surprises us every single time we look at it. Every time we measure something new, we find out something about it, and it's just the sort of human desire to understand everything that's around us.
If there was someone who knew nothing about Venus, what would be the one thing you would want them to know? What's the most exciting fact about Venus?
Well, I mean, there's way too many to just have one, right?
Okay, what two?
Okay, let's do two each. Yeah.
Okay, my first thing would be active volcanoes. I think that is very much the holy grail, and I think they are there, and I think it's going to be very exciting when we are able to detect them and actually keep an eye on them.
I think it's the fact that it's the clouds. You know how here we're always waiting for the sunny day? I mean, the clouds are like 20 kilometers deep. They're around the whole planet all the time. So I would put that as my first one. And do you have a second one?
Yeah, I think the big one is of course the ocean question. You know, we want to know why the ocean went away there. Did it in fact have an ocean? Are we even more unique than we thought? You know, did Venus not have an ocean? Did something change about that in its formation history? Those are all sort of the big fundamental questions of how you build a solar system, and of course how you would build an extrasolar system.
Yeah. And on the question of building a solar system, you know how Earth got whacked that made our moon, but Venus must have had a much more serious collision with another object because it rotates the wrong way and it rotates incredibly slowly. Its day, its time to rotate, is longer than its year, the time to go around the sun. So I would highlight that as a fact we want people to know how crazy that is.
And just in that vein, when we talk about needing radar for Venus, if you want to know how quickly Mars is turning, you can take a large enough telescope and you can watch a spot go by. But because Venus spins so slowly and it's got the clouds, you have to use a radar system, and you have to watch for a very, very long time, because if you want to measure very precise, numbers within a 243-day day, then you've got to see it over a long period of time, like tens of years. And even very small measurement errors in that can end up where you think you might be landing at a certain longitude and you might land 20 kilometers away, 30 kilometers away. So it's an interesting use where especially Earth-based radar has helped to narrow down that spin rate.
Wow, and since he took a third, I'll just do one more.
Please.
So, Venus is rotating so slowly, as Bruce was saying, it's really hard to, make a measurement that, yeah. Well, the atmosphere, up in the upper atmosphere, it's whipping around in 4 days. The winds are so incredibly strong, so.
Yeah, so that's incredible. So whipping around really fast at the top of the atmosphere, and then, as you said earlier, very calm breezes on the surface, right? So that's a pretty big difference.
Well, and that is a good lead into when we talked about the fine material on the ground. There is this question of if you see sort of dirt around you, is the dirt all just local? And until the Magellan mission, we really didn't understand. In a very thick atmosphere, you expect an impact crater is not going to throw material very far, right? It's got to push through the equivalent of 3,000 feet down in the ocean. It's not going to go far. But as it turns out, anything that goes up gets carried a very, very long distance, and in some cases 2,000 kilometers. That material will go up into the upper atmosphere and it will rain down 2,000 kilometers away. And so most of those dark patches in that map are crater-related fine material that as the stuff went up, it just came raining back down. And we think that over the planet, probably one of the dominant sources, if not the dominant source of fine stuff around you on the ground, sort of sand or dust, is coming from craters that might be very, very far away from you. And it's all thanks to that upper atmosphere super rotation.
Wow. On that note, I'm going to shift over to our audience Q&A now. If you haven't already submitted your question, the QR code is behind me right now. Let's see. We have one audience member who asks, can you describe the surface of Venus in more detail? Are all the rocks volcanic? What color are the rocks? How much dust is there? Is it a smoky area? You know, if you could go into more detail to describe what you would see if you could somehow stand on the surface of Venus.
Well, again, our sort of knowledge of all of this is the 4 postcards. So to the extent that they are representative, the colors are relatively dull color. They are mostly gray to black rock. Chemical analysis suggests that they are probably basaltic, so they're very similar to rocks that you would see in Hawaii if you're out on the volcanoes there. In terms of the appearance, everything is very murky. The horizon looks very close to you because there's so much refraction in the atmosphere that you really don't, what you seem to see is much closer to you. And then one of the interesting things, if you're actually on the surface, is the fact that there are no true shadows because the light comes from everywhere all the time. Day and night only consists of the light getting brighter across the whole sky and the light getting darker across the whole sky. It's not like the area where the sun is gets brighter and that moves around. The light's from everywhere all the time. So the only shadows that you see in this picture are the fact that an area doesn't see as much of the sky as areas around it. So if you're tilted this way, kind of leaned over, you don't see very much of the sky, so you look dark. But it's not actually a shadow in the same way we would think of it.
This question, I think, is for you, Sarah, because it's about private Venus mission, the Morningstar missions, I presume. What new scientific instruments or technologies will the Morningstar missions have that previous missions have not?
Alrighty, well, the Morningstar missions to Venus is what we call our international consortium, where we're trying to do small focused missions to Venus to search for signs of life. These are complementary to the bigger NASA missions and ESA missions we'll hopefully be hearing about in a bit. Well, our first mission to Venus in the series, we call it the Rocket Lab mission to Venus. If you could please pull up the slide that shows, I think it's like the people with the little, our first mission to Venus, it's a small mission, and this is the real probe that will be dropped off in Venus by Rocket Lab. And this probe, you can just see how big it is. It's about 40 centimeters across. It's not going to open. It is just going to go down, rushing through the atmosphere and slow down based on its own drag. You can see a hole in the outer probe, and you can read this chart if you want. It's just going to spend 5 minutes in the clouds. And the single instrument that we have, it does have heritage from the past, and it's not necessarily brand new, but we're going to shine a laser through the hole, and we're going to be looking for fluorescence in these cloud particles. Just like if you know in a kid's fun house or nightclub when you light things up. And this fluorescence is going to indicate whether or not there are organic particles, like especially ringed molecules are very easy to fluoresce because they share electrons that can be easily excited. We're going to be measuring the backscattered polarized radiation to confirm past findings that it's not pure sulfuric acid and the size distribution and as well. That's the first mission to Venus. Here you can see the pressure vessel and our instrument. We call it the autofluorescence nephelometer. I always think nephelometer is like for kidney, but it's a cloud probe. And that's the pressure vessel, and there's the instrument. So we're trying to go back and interrogate the clouds, but our first mission is also to show that a small team can do a small focused single instrument mission. Our future missions will include newer technology that we're developing now that hasn't yet been deployed on planets. And specifically, we're after trying to identify very complex organic molecules. But traditional methods we tend to use, they actually are very ambiguous because a lot of molecules have similar signals. So we're trying to accelerate development of miniature molecular sensors. Each would be targeted to a specific organic, and we would hope to send like 10,000 miniature molecular sensors all integrated into the bottom part of the probe as it's falling down through the atmosphere.
And Bruce, I think following that up, with the Veritas and Da Vinci missions, can you talk more about sort of how that fits into this sort of longer history or heritage of missions, including ones like, say, Magellan?
Sure. Veritas, just to start at that end of time, Veritas is going to give us a global image map with about a 30-meter resolution, and it's going to measure the topography of the whole planet down to about a 5-meter accuracy. And that's going to be a remarkable data product because a lot of the data we have from the prior mission, from Magellan, in the sort of circa 1990 range, it's wonderful radar imagery, but radar has some limitations that it won't simultaneously give you a picture of the terrain and tell you the heights of the features within that picture. It's ambiguous in that way. Veritas uses a technique called interferometry that will simultaneously collect basically 2 radar images. There are antennas on either end of that swept wing, and by using those 2 antennas at the same time, you can get a simultaneous image of the surface, and you can measure the height of the ground. So you can put together a much more geologically important type of product. And this builds back to Magellan's products, which also had a radar altimeter, and then back to Pioneer Venus Orbiter in 1978 that had a radar altimeter. Little by little, we've built up a progressively more sophisticated map, and Veritas will take us that next level to a global high-res product and topographic map.
I'm going to add a question of my own because I have the microphone. My question is that in addition to those dedicated Venus missions, Venus has also been used by other spacecraft for gravity assist maneuvers and, to help them reach places farther out in the solar system. Have those flybys, also contributed to our understanding of Venus, or were they really just there for the boost?
I'm not aware. I know that there have been some imaging spectrometer testing that has been done as spacecraft flew by. I'm not aware of an awful lot beyond that in terms of just gravity assist missions. I mean, obviously, if you want to do radar in particular, you've got to be quite close. It's got to be typically less than about 400 kilometers or so above the surface. So most flybys aren't bringing you down that low to where you, even if you had a radar, you wouldn't be applying it there.
We have a question about Venus's magnetic field. One of our audience members asks, does it have one? And how does that compare to Earth's magnetic field?
One of the findings of Mariner 2 was that the magnetic field, if it exists at all, was very weak, and a further Pioneer mission later on confirmed that it was really very weak, hundreds of times smaller than Earth's magnetic field. And my guess, and I think it's probably a fair guess, is the fact that when you have a very slow spin rate, you also are not able to have a dynamic fluid core dynamo going on, because that's what drives a planetary magnetic field, is to have motion and currents formed within a liquid core of the planet. Part of that is driven by the fact that you've got rotation going on to help drive that. So my assumption is that because you don't have that spin motion, you're not generating a strong magnetic field. But it does have implications for the fact that you don't have that strong magnetic field sort of holding off the solar wind and other things that it does for the Earth.
And we have a question about the atmosphere. Does Venus's atmosphere have layers the way that the Earth's does?
Let me think. I mean, yes, it does have layers like the Earth's do. And, photochemistry plays a role and kind of marks the higher atmosphere.
All right. And a question about someone who wants to know more about phosphine. How could it support life, is what they ask.
Okay. So phosphine on Venus, it's not that it would support life, but the question is it a sign of life? Because our premise in the search for biosignature gases, we call them, are gases that shouldn't be there. where there's no known chemical explanation for it. And phosphine, particularly, when we worked out, like, how might it be produced by volcanoes, or if there's lightning, or delivery by meteorites. And no process we know could make the phosphine in the amounts, even though they were tiny amounts reported, though that report's controversial. So it's not so much that it enables life, but that's a gas that shouldn't be there. Just like oxygen in our atmosphere, which should react away and therefore would have to be continuously produced by life. So it's a sign of life rather than helping life.
Mm-hmm. And we have another question about sort of possible future technologies. Would it be possible to build the equivalent of a sort of Venus atmosphere helicopter type vehicle, sort of, we've seen the introduction of rotorcraft on Mars. We have the Dragonfly mission coming up. Is there a way to operate in the clouds of Venus for a more sort of longer period of time?
Well, I don't know that a helicopter would be your choice, just because, remember, it's so incredibly windy. And I don't know if we have a great handle on how turbulent it also is. But certainly, we know that the former Soviet Union sent 2 balloons to Venus. They sent the Vega balloons, and those lasted for 2 days each, just on their own battery power. So there definitely has been a big contingent of the Venus community wanting to send balloons to Venus, balloons that could last months or even longer.
And there have been studies and even some mission proposals quite a while back about aerobots, with basically a balloon that you could deflate and inflate. And so you would have your sort of descent sphere on the bottom of the balloon. You would deflate the balloon, you would go down to the surface, you'd spend as much time as the spacecraft could tolerate, then you would go back into that area in the clouds where it's more like room temperature, normal Earth conditions. You'd let the temperature insulation congeal again and provide that support again, and then you would descend and do another study. So you would travel with the wind, and then you would go down, come back, go down, come back. And that kind of technology is reasonable, that something like that could be achieved.
People have also talked about, like, planes that, a plane-like structure that could go down and come back up, maybe get some more solar power and then go down again. They can't go too far down into the gravity well, or they can't get back out. But there's a lot of ideas. People really do love the idea of being in the clouds for a while and sampling.
We have another question about, if you had your sort of druthers, what would be the wildest fairy tale fantasy experiment that you would conduct related to Venus? And, is that even potentially possible? What equipment and resources would it require?
Well, I did mention sample return, and NASA does have a really nice program called NIAC, which sponsors those kind of crazy ideas. In fact, if it's not crazy enough, you'll get rejected from the funding source. And we did get a phase 1 to study this idea. So I'll just now go into a bit more detail of how crazy it is. So you'd have to go to Venus with a big entry vehicle, open that up, have a giant balloon. And the balloon has to be giant because attached to it's going to be, let's say, a tiny rocket. But even a tiny rocket is thousands of pounds. And so this balloon is so giant, and it will have its own parachute. But as it goes down, it has to inflate. Because if it gets too far down and inflates, it won't be able to come back up. It'll be inflated with helium. And so that balloon, I think, is super hard to imagine. Although here on Earth, we launch these giant balloons, so maybe it's feasible. So then we think we know how to collect the clouds and store that. But now we have to launch a tiny rocket off of like a crazy moving platform. Now here on Earth, there's been a company called Raccoon that wants to launch like a rocket from a balloon. So maybe we could get some of that technology can develop on its own, right? Uh-huh. But launching from something that's like moving a lot, and then it has to launch precisely, right? Because it's got to get to the right orbit, and that has to connect with the orbiter, and that whole thing has to come back to Earth. However, with the Mars sample return, I know it's on hold right now, but we hope other sectors can get other things done for us, like Raccoon and like sample return from Mars, and so some of the hard things can be done, leaving us with, that's what I tell my team, one miracle. Hopefully it leaves us with one miracle to solve. So sample return of the clouds to look for life.
I think for me it would be a long duration rover that could climb through the mountains and really find us that evidence for how did those form, is there evidence of the past climate, and even understanding the current level of activity on the planet.
So both of your answers, I think, mainly just involved robotic technologies. And we have a question about humans. You know, I think we know that it's not really possible for humans to live on the surface of Venus. But so I'm going to change the question a bit. Would there be great value to building, say, the equivalent of a space station orbiting Venus as sort of a Venus orbiting observing station? Would there be a benefit to having humans that close to the planet?
I think it would depend on if you had the availability of a lot of additional landers and atmospheric sensors and sample return vehicles. If that was sort of the hub for all of that, I could see where
Yeah,
where
some
that would
people have
drive it.
proposed like having a laboratory in the Venus atmosphere where samples can be brought up. But there are people who want to see humans on Venus in the clouds, like in large space habitats. I don't know if anyone would choose that as like a tourist destination, but the point is that although there's not the right air for us to breathe, it's the right temperature and pressure and the same gravity as here on Earth, so there are some good reasons.
We have a question about whether Venus and sort of the path that it has taken as a planet has anything to tell us about what could potentially happen to the Earth. Could Earth go that direction and become uninhabitable and, you know, hot and unlivable?
Well, from everything we understand about physics and chemistry, our Earth will not get that hot. Like, even though we talk about climate change and we all see it like in our lives, like from, you know, as the decades go by, we're not going to pass that tipping point where all of our oceans are going to evaporate. However, there is a time when we won't be here, billions of years from now, you know, when our sun runs out of fuel, and our sun's going to be done being on the main sequence and steadily burning hydrogen, and eventually our sun will expand. And that's the fate of our Earth in the far future, where our Earth will get hotter and hotter as our sun expands and eventually engulfs Earth. So it's far from now, so you don't have to worry too much. But just to assure you, we can't push our climate that far as humans, like past that tipping point.
Well, I think we're pretty much out of time for the evening, so what I'm going to do now is remind our audience that the next lecture at the museum is not part of this series, but we hope you all will join us. It's my colleague, Dr. Mike Hankins from our Aeronautics Department, who's going to be joined by 3 members of the 53rd Weather Reconnaissance Squadron, also known as the Hurricane Hunters. And they're going to be talking about the work they do storm chasing. That program's going to take place on May 20th here at the museum, so register now. And then after that, our final Exploring Space lecture, Our Future on Mars, is going to take place on June 3rd. So please register for that. Tonight, stargazing will take place outside over by Delta Solar. So just head out the Independence Avenue exit and walk towards 7th Street. Our astronomy team is going to be waiting for you. And we want to hear from you. If you would take a few minutes to complete our lecture survey, we'd really appreciate it. The QR code is behind me right now. I want to thank our speakers, our guests tonight. Thank you, Bruce Campbell, Sarah Seeger, for joining us. And thank you again also to our sponsors, L3 Harris and United Launch Alliance. And thank you, our audience, whether you're here in person or watching online. Thank you for coming and participating. We're always happy to have you here.